The title of my talk is From Matheron's Theory of Regionalized Variable to Exascale Geostatistics. Okay, I wanted to start just by giving you a picture taken in Saudi Arabia at KAUST, at this university that opened up in 2009. And when I joined in 2012, I had the opportunity to build a statistics program from scratch. This picture is pre-pandemic, but currently we're around 70 statisticians. This includes student, postdoc, research scientists, and faculty. So I plan to talk about the following 4 topics. First, I would like to make a couple of remarks about Matheron's theory of regionalized variable, and this will include robustness and efficiency in variogram estimation, talk about a model that transitioned from second order to intrinsic stationarity, and also a little bit about transform Gaussian random fields. And then I'll talk about large-scale stochastic generators, some visualization tools with apps, and finally, the software ExaGeostat that we're developing at KAUST for geostat at exascale. So I thought I would just have a few bullet points about Georges Matheron, because I guess the most senior people in the audience will know that, but maybe the more junior won't. So Georges Matheron was born in 1930. He passed away in 2000. He was a French mathematician and mining engineer. He's very well known as being the founder of Geostat and co-founding mathematical morphology. He studied at École Polytechnique and École des Mines de Paris with Paul Lévy as advisor, so naturally he would be working on stochastic processes. He worked in Algeria. He coined krigage or kriging in English to honor the mining engineer Danny Krieg. In 1968, the Paris School of Mines created the Centre de Morphologie Mathématique located in Fontainebleau, and Matheron was the director. And what I found very interesting is that in 1970, Georges Matheron, in fact, met with John Tukey at a colloquium at the University of Kansas. John Tukey is a very famous statistician. He invented the fast Fourier transform. And he happens to be my academic grandfather, so I have a link to him. And you will see further links a bit later on. Also, interestingly, John Tukey was a little bit older than Matheron. He was born in 1915, but he also passed in the year 2000. So the first part is about robustness in variogram estimation, and this was a very nostalgic point here for me to go back to one of my first papers taken from my PhD thesis at EPFL and published in Mathematical Geology in 1998. The journal now is called Mathematical Geosciences, and the title was Highly Robust Variogram Estimation. And on the second page, the framework was of intrinsic stationarity, where you have a process Z that has a constant mean over the domain, and the variance of increments of Z at x plus h and Z at x would depend only on the lag vector h separating the two locations, and this was called the variogram. And so with a constant mean, this variance of an increment is also the expectation of the square of the increment. So very naturally, you estimate this expectation with an average. So Matheron's proposal here was naturally to average the square differences. This is a very nice estimator. It's unbiased. So whatever the distribution of Z, the expectation of that estimator will give you this variogram quantity here. Unfortunately, it's not robust to outliers. So if you have contamination in your data, this will affect the value of your estimator in a quadratic fashion. So in 1980, Cressy and Hawkins proposed an estimator they call robust and defined in this fashion. So basically now you take the square root of absolute value of increments and do some corrections. But the problem is that this estimator actually is not really robust. So the influence is as a square root instead of as a square, but it still has an unbounded influence. So if you want to get a bounded influence, you need to do something else. And the proposal here was to look at estimator of scale. So the highly robust estimator here is the square of that scale estimator Qn that is defined here. Essentially what you do, this V of H is an increment at lag H. You look at the difference of two such increments, and any such difference in absolute value would be a scale estimator. But what you can do is to pick one particular such term. So you order this difference in absolute value and you take a quantile k. K is about 1/4 if you want. And by doing so, you have very strong robustness for this estimator, and you have also very high efficiency. So the variance is fairly low. So the point here is that really, if you're worried about robustness, I'm not saying this is the best estimator ever, but my suggestion is that you compute Matheron's estimator, you compute this highly robust estimator. If both are fairly similar, then you will say, well, probably you don't really have to worry about outliers in your data. If they look quite different, then maybe you need to look a bit more closely at the value in your data. The second remark is about the efficiency in estimating this variogram. And to do that, just start very briefly by telling you about this tool for visualization that we introduced in 2011 called the functional box plot. You know, in some cases, your observations are not just one-dimensional or multivariate, but they can be continuous function. And this is a case where you look at sea surface temperature in the tropical Pacific Ocean as a function of time here in months. So each curve represents 1 year of data. This is one observation. So you could summarize this with a box plot where essentially you rank these curves. The deepest will be this curve in black. It's the median curve of that sample. And then you can construct a box by taking the envelope of the 50% deepest curve and so on. You can flag outliers. I hope you can see you have some whiskers here in blue, and in red you have these outliers. There are unusual years there, so-called El Nino years. And we have code in both R and MATLAB to do this very efficiently. I'm mentioning this because this functional box plot is good to summarize data that come as functional data, but also in many settings you have functions. Just think about geostat, where you're looking at variograms or covariograms or other type of curves that naturally occur. So here's a toy example where I consider an exponential variogram. There's only one parameter here, theta. The true range parameter, theta, is 0.25. And I'm going to simulate realization from a Gaussian process in the unit square at 400 random locations. And then I'm going to estimate this parameter theta by either ordinary or weighted least square methods, or by maximum likelihood under Gaussianity. And I do this 1,000 times for each. So for each of the three methods, I'm going to get 1,000 estimate of the parameter theta. And if I plug those in that function, I get a curve. So I get 1,000 curve for each method, and I can summarize and visualize this information with this functional box plot. So if you see here ordinary and weighted least square, you see weighted least square is going to improve a bit the variability, for example, measured by the height of this box in magenta. The true underlying variogram is in green here. I'm not sure if you can see this very well, but visually you can see that if you use likelihood-based method, then the efficiency is much better. So this means you have much less variability in the estimate of this parameter. Of course, this is a toy example. We have many more complex situations with more parameters and also looking at non-Gaussian cases. And it turns out that in most cases, this likelihood approach are preferred. And this was the motivation also later for looking at this ExaGeostat software based on a likelihood method. So that was my second remark. The third one is about a model that I think is quite cool, and that was published in the journal Stat. So maybe it hasn't reached the Geostat audience, so I wanted to mention it here. It's a variogram model that has two parameters, alpha and beta. So alpha has to be between 0 and 2, and beta can be negative or up to 2. And what is interesting is that this variogram model is bounded if and only if this parameter beta is negative. So this means it can vary from being bounded to being unbounded. So to go from second order stationarity to intrinsic stationarity. And so you can estimate this parameter beta from the data. And with my student, we have extended this model to the multivariate case. Here you have a little animation where here you have a set of possible value of the two parameter alpha and beta. The blue point corresponds to these two values, and the point is going to move here. In this plot, you have the direct variogram in red, And in this one, you have in red the traditional cross variogram, or in blue a pseudo cross variogram. And if you look at this animation, you can see that the behavior, depending on beta being negative or positive, is changing from bounded or unbounded variogram. So this was just a short remark that I thought maybe would be interesting for this audience. And the last point here is about a transformed Gaussian random field. So this is my link with John Tukey here, who proposed in the 70s this, so he could have discussed this with Georges Matheron, this so-called now Tukey GNH transformation defined here, depends on two parameters G and H. G is a real number, and this transformation is strictly monotone if H is positive. So this is what we usually consider. So if you take now a random variable that is standard normal with mean 0 variance 1, you apply this Tukey GH transformation, you multiply by a scale omega at a location C. This new random variable Y is said to have a Tukey GNH distribution. And it's very flexible. It includes the log normal distribution. And it can approximate other distributions such as the student T, Cauchy, skew normal, and so on. So very naturally, we could do this also to random fields. So this is what we propose, to define a Tukey GNH random field. You apply this transformation to a standard Gaussian random field Z with mean 0, variance 1, and a certain correlation function. And then you can do Kriging in this resulting field. You can study how you do likelihood inference and so on. You can even do this in the multivariate setting as well. What is interesting is that you can estimate these two parameters G and H with the other parameter of your model of your correlation function. For example, G controls the skewness and H the tail behavior. So it's, again, it includes the log normal. So it includes log normal random field as a particular case, but you estimate the optimal transformation in that family. And here you have some realizations. So this is just both G and H are 0, so this is just a Gaussian random field with a Matheron covariance function. Here G is 0, H is 0.2, so the tail are heavier. So what was kind of orange is more red, and when it's white, it's just that it's beyond this limit here of the color scale. And what was light blue is more dark blue, so you're pushing to the tail. And if H is 0 and G is, for example, 0.3, you bringing skewness, so asymmetry to the right. So things become more red and less blue. And the reverse, if G is minus 0.3, value become more blue and less red. All right, so that was a couple of remarks I wanted to make related to Matheron. Now, in this second part, I want to talk a bit about large-scale stochastic generators. And the motivation for that comes from wind energy. The potential is very big, in fact, in Saudi Arabia, and there's a plan to get by 2032 54 gigawatt of renewable energy, of which 9 gigawatt and now actually 16 gigawatt should come from wind. The question then is, where do you locate those wind farms? There are very few observations of good quality, and the land is very big. So how do you decide on those? Well, we're basically going to use climate models. So in a nutshell, a climate model is a very complex, in fact, mathematical model that tries to reproduce geophysical processes on a global scale, so on a sphere, on Earth, via a system of PDEs. And of course, there will be input to this model. They come from different future scenario of emission that you want to consider, and also initial condition of put on the PDEs. So you want to ideally run this climate model several times. And you see here a representation where you need to model what happened on land, ocean, in the atmosphere, the ice in sea and land, and all linked together. So this climate model are used to make projection of future climate. They are uncertain, they depend on initial condition. We need to assess the associated uncertainty. But as I hinted at just before, this is actually very costly. I mean, it's costly in time. Maybe you need to run the climate model for several months to get one output. And also it's very expensive. You need a supercomputer. This is very expensive to buy, to maintain, to store the data and so on. So that's a motivation to build stochastic generators. So essentially we're going to use only a few runs output of the climate model. We build a stochastic generator. The simplest is to say that the wind vector for the realization, the run number R, just comes from a very big multivariate Gaussian distribution with a mean and a covariance matrix parameterized by parameter theta. If you can estimate these two parameters, then you can simulate from that model, and you don't need to store all this output from climate model. You don't need to generate many runs, but you can simulate very quickly. And this is important because now we are in a setting of big data where the output of this climate model are typically huge. Another point to make is that the Gaussian assumption is not always suitable, especially at relevant for policy making scales in time, such as daily or monthly data. So we're going to build a fairly simple model in some sense, but that will capture this non-Gaussianity as well. The data that we consider here are output from the LENS project at NCAR, the National Center for Atmospheric Research in Boulder, Colorado. There we have a set of 40 runs, but we're going to use just 5 of them. Those are near surface wind speed from 2006 to 2100. So we're projecting this in the future. And this leads already to 220 million points. You have on the left a plot of the ensemble mean over those 5 runs. And you can see, so red is strong wind. So you see that wind is stronger, of course, on ocean than on land, where it's more kind of bluish. And this is a measure of the standard deviation over these 5 runs. Now, the mean and variance and covariance are not enough really to describe this data. Indeed, if you compute at each location the skewness here and the kurtosis over time, you will see that there is strong asymmetry and tail behavior as well. So here, for the skewness, what is white would be 0, so symmetry. So you see that still many regions are either red positive or blue negative skewness. And the kurtosis, what is white would be 3, so like the kurtosis for the Gaussian. You see there's a lot of red, in fact, in many locations. So this suggests that we should try to model skewness and kurtosis for this data. So the model, just in a nutshell, is quite simple. We're going to remove a trend. We subtract the average over the 5 runs. And then essentially we have a Gaussian model transformed with this Tukey GH transformation I mentioned earlier, and you have location and scale, basically. How we fit this model, we cannot fit those 220 million points all at once. We do this in a multi-step fashion. So we look at each location first on the Earth. So here's just a schematic representation. A red dot is one of these locations. We fit a time series there separately. We can do this in parallel with distributed computing. And then we look at the fixed latitude, and on this circle, we stitch these points together with a certain covariance that will be of matter and time, but in the spectral domain, because we're using the fact that we have basically equispaced or regularly located locations. And then we can do this separately for each latitude. Then we have to stitch together this different latitude. And if you have information also about height, you have different height here in the atmosphere. You can then stitch them together like an orange peel at different levels. So we've done that exactly for this model. And if you want to see whether this Tukey GH type of model is better than the Gaussian, you can, for example, look at difference in DIC as a measure of fit. And what is red means that it's a better fit. And you see that in most locations is actually quite red. And so you have an improvement if you use this Tukey GH transformation. Eventually, we're interested in wind power density at, for example, 80 meters, which is a typical turbine height. And so here you have a plot of this wind power density This is in March 2020 and in September 2020 in the Gulf of Aden. The output from the 40 runs would be these black stars. We use only 5 of them. And with this, we fitted this stochastic model and we simulated from it, for example, 40 realization. And the histogram in blue represent this simulated realization with a non-parametric density estimator in red on top of it. And you see that you can capture fairly well that distribution. So these data were generated based only on the 5 red plus signs, and they mimic somewhat what's happening in all the 40 runs from the climate model. So the point is that we don't need to get these 40 runs. We could just use 5, for example. And finally, some dynamic diagnostic. You could compare the output of the stochastic generator with the data from one of the runs. So this is with year going by, and you see, of course, they're not exactly the same, but they have the same characteristic or distributional properties, and this is what we are looking for. This brings me to the third part here, where I wanted to say something about visualization. The idea here is that we could use our smartphones to visualize output of our models, and this is an example. In fact, if you have a smartphone, you can download now or later on that app. It's called Statistical Emulator. So if you look in the App Store, you will find it. There should be one also for Androids, but I don't have. I have an iPhone, so I'm more on iTunes here. And I'll tell you just a little bit about that in a few seconds. So it's a similar type of problem as I described before. This is actually for temperature on Earth from 1850 projected to 2100. We have the output of the climate model here and the emulator or the stochastic generator here. This is at the surface here, but we have actually 17 different layers of altitude. This in total represent 1.5 billion with a B observation to fit that we fit in this sequential fashion. So here you see in the movie the years going by and the CO2 increasing with that particular scenario. If you have the app, you can look exactly at that output. So you have the output from the climate model and from the emulator. You can, with this button, rotate these spheres. You can magnify them. You can change the altitude, the speed at which the year go by. And there's a VR mode. So if you have, these Google apps, you take your phone, you can put it there, click on VR mode, and you can look in 3D at those two spheres and at the behavior of the emulator, the stochastic generator, compared to the output of the climate model. And there's another one called global surface wind, and you could look at this as well if you're interested. So the idea here is to bring basically the output of the research to maybe an audience at the conference, but also more generally to the public, and they can see visually the result of some of the experiments here. Of course, this lens data is actually very coarse. The resolution is 100 kilometer by 100 kilometers. Over Saudi Arabia, you see that you have only a few pixels. This is not enough for us, so we need to run ourselves. So this is publicly available, but we have to run ourselves with a WRF model, high resolution here over Saudi Arabia. This is 5 by 5 kilometer resolution, and this is what we need to really better understand where to place wind farms and things of this type. So the last part here is about geostat at exascale. So this software ExaGeostat we're developing at KAUST now for a couple of years. Essentially, what happens is that when data set becomes large, the number of observation n becomes large, then essentially you're dealing with large covariance matrices. And if you want to do a likelihood inference or kriging, eventually you'll have to deal with either Cholesky factorization or some kind of computation that tend to take order n cube floating point operation or n square memory And therefore, those settings when n is large, high performance computing is helpful. And the software that we have developed is meant for that. So you can run it on your laptop, on your desktop, on a cluster of a computer, but also on a supercomputer if you have access to it, and on the supercomputer of tomorrow that do not yet exist, that work at exascale. They are designed for that. So we have two GitHub, one for ExaGeostat, this is the C version, and ExaGeostat R for our users to be able to access to this software. Basically, the current version can do likelihood inference. It's based on the Matheron covariance, can do spatial interpolation of kriging, and simulation of random field. We're building more and more feature, including multivariate model and space-time covariances and some non-Gaussian model as well. Of course, there are many approximation methods that have been proposed in the literature to ease computational burden. And in fact, we organized a competition on spatial statistics for large data set this year. There were 21 teams from all over the world. There will be a paper with discussion that should appear soon. And I mean, you can look at more details about that. The advantage with ExaGeostat is that we can do exact computation for very large dimension that other software cannot do.
Mark, this is just a 5-minute warning.
Yes, thank you. So what is high performance computing? So in a nutshell, it's the use of parallel processing for running advanced application program efficiently, reliably, and quickly. Ideally, you have also access to accelerator, for example, GPUs, and typically HPC is applied for system that can function at teraflops or order 10 to the power 12 floating point operation per second. So teraflops is here. So all this here would be called HPC computations. ExaGeostat is able to run at that scale, so 10 to the power 18 operations per second. So this is 1 billion. So the repeat was not a typo in my abstract with B, operation per second. Such a computer does not exist at this time. There should have been one coming out in the US this year called Aurora. I think it's being delayed to next year. But basically, the software is ready to run on such a computer. The fastest computer today is the Japanese Fugaku. Is ranked #1. It has around 537 petaflops theoretical peak performance. You see more than 7 million cores. But of course, it's very costly, costs about $1 billion. You can think, I mean, here's a picture of that supercomputer. It's very big, it takes a lot of space. You can think about it as putting 20 million smartphones in a room and doing computation with those, or 300,000 standard servers in the room and doing computation with those. There are many other supercomputers. The second is Summit in the US, and other countries have their own supercomputer. At KAUST, currently we have Shine 2. It used to be in top 10 when it was bought a few years ago, but very quickly goes down the rank. We are trying to get the next one in the next couple of years. So to tell you something about how the covariance matrix is stored in ExaGeostat, of course, this is the lower part of the covariance matrix. It's broken into tiles. These are stored in double precision. So this for exact computation. You can do some tapering where some you set to 0. You can do what we call tile low rank approximation. So these tile in the lower part are approximated by low rank matrices. And you can also play with double, single, and half precision. For example, here, the one in blue are stored in double precision, those in single precision or even half precision. So you have much less storage. You can do faster computation and so on without losing too much accuracy. I mean, that's the goal. So I'm almost out of time. This is just a timeline. We started in 2017 with this project. We developed this tile low rank approximation in 2018, mixed precision in 2019. COVID year, well, we still did some work on multivariate and and other extension. And now we're looking at hierarchical matrices to do further approximation as well in the software. And just wanted to let you know that if you're interested to read more about that, probably the best paper to read first is this one. It's not in the stat or geostat literature, more in IEEE heat transaction on parallel and distributed systems. So I think that's it. So I talk about these 4 parts, some remarks first about Matheron's theory of regionalized variable, essentially robustness and efficiency estimation in variogram estimation, this model that transit from second order to intrinsic stationarity, and this transform Gaussian random field with the 2-key GH transformation. I talk also briefly about large-scale stochastic generator. The motivation was for wind applications, and also about visualization on smartphone. I hope more people will try to develop this further. And finally, I describe a little bit about the project ExaGeostat to do geostat at exascale. So thank you very much for your time, and I'll be happy to answer any question you may have. Thank you.
Thank you very much, Marc. And if anybody has a question, I'm just looking at the chat. So if anybody has a question for Marc, we have a little bit of time just before our next speaker comes on. So I'm absolutely fascinated that the Matheron lecture right up to present day and VR on an app. I think it's phenomenal. Just while we wait to see if there's any other questions just before our next speaker. So in terms of your modeling, and obviously it's the speed, but how much interaction then do you have with the current climate modeling and all of the current modeling? So how is your approach being adopted, or is there work to integrate or to adapt?
Yeah, so there is, I mean, we're interacting with climate scientists at KAUST, but also at NCAR. And in fact, in one of these wind projects, I have also former postdocs who are now faculty in the US, and they are atmospheric scientists, and they are involved in this project as well. So we don't do it just by ourselves as a statistician. Yeah, I think there is interest in this idea of replacing many runs by surrogate runs, and also use this as a compression scheme, because then you just have to store essentially the parameter of these models. And if you need to create new runs, you simulate from this model, and these simulations are very fast. So I think there is interest, whether really things have picked up and climate scientists are using this. I'm not sure to what extent.
Thank you. And there's a question from Gerald that sort of asks about the relative performance of Turkey's G and H transform in a non-parametric Gaussian transformation. Do you have any comment?
Yeah. Yeah. I don't know exactly.
Gerald, if you want to ask.
Yeah, I would say that probably, I mean, okay, I'm sure there are models that cannot be captured by this 2-key GH transformation, and perhaps a non-parametric transformation can capture better, at least a little bit better. So this is a parametric model, a parametric transformation, but as I said, it's very flexible. It includes the log normal. So given all the work on log normal random field, I think this is something of interest. And you have these 2 parameters that have very clear interpretation, G controlling the skewness and H the tails. So this means that you have this interpretation, you can say something about what's happening in your model, you can control those, and you can use these also for simulation and kind of vary them if you wish. So yeah, I kind of like that transformation, but I'm sure you can also use other transformation.
Okay, Gerald, do you want to come in on that just briefly? Do you want to follow up with anything? Just
yeah.
And Marc, I might ask you to just stop sharing the screen for the moment while we get ready for the next presenter.
Mainly, I just thought that is a more has less parameters, so it might be a better performance if it's the right model.
Mm-hmm.
Then you might be able to quantify how much better it is.
Yeah. Yeah, that's right. But as I mentioned, I mean, it's a class of distribution. It seems to be very flexible to approximate many distributional transformations, but of course, it does not exhaust all possible transformations. So if you outside of that class, then I'm sure maybe you can have other transformation that might be better.
Yeah, but if you're inside the class,
Yeah.
maybe you could say how much better is that than ignoring that you know the class.
Yeah.
Yeah.
Yes.
Thank you. Thank you very much for the very interesting talk.
Thank you, Gerald. And Regina, just checking, has Peter, have you joined us on the call? Regina, has Peter Atkinson joined us? I don't see his name on the list.
I don't see him too.
Okay, is it possible to give him a little email or prompt, just in case he's having issues getting through?
Okay, I tried.
So just while we wait, I think that Greta is still on the call, and obviously if Marc is still here. So has anybody, we didn't have a lot of time after Greta's presentation, so has anyone any comments or questions for Marc or for Greta while we just wait to make sure that Peter can get connected? So I'll maybe follow up a little bit, Marc, and just on one thing that, and it's, you know, it's not, it's connected to your talk, but obviously it's not as connected to the statistics, but perhaps it is. But I'm very aware that there are other variables, especially in locating wind farms globally, that are not just connected to the wind power, but are obviously connected to the land use. And they're generally on upland sites, and across certainly Europe, there's an issue of peatlands and where they are. And the other thing is that for every wind turbine we erect, there is how do you decommission and reuse and repurpose the wind turbine blades. So it is, you know, away from your topic, but do you think that statistics, geostatistics will be able to, or how do you think it's also, or it should be part of any putting up of a wind turbine farm installation, should the decommissioning should be part of it in a sustainable energy future? Any thoughts or comments on that?
Yes, of course, you're absolutely. Oh, yes, I'm on, right? Yes, you're absolutely right. I mean, it's not just. I mean, what I have shown is a bit simplified. I mean, some part of the story, things are much more complex. I mean, especially in Saudi Arabia, you have to take into account proximity to roads, or you have to take into account the terrain, and there are many other variables, the type of turbine, the type of height. But we have actually a study where we have looked at all that and basically come up with a blueprint for Saudi Arabia of what would be an optimal layout. Maybe I put here, let me see in the chat, just a link to that paper. It's published in Applied Energy. And so this is a big project that I have jointly with collaborator at the University of Notre Dame. If you're interested, you can read a bit more on that. But you're absolutely right. I mean, it's much more complex than what I described here.
Brilliant, thank you. Are there any more comments for Marc or for Greta? Just while we wait for Pete to join us. Regina, any word from Pete that he wasn't able to join us?
Must be a mix-up with the time zone.
I know we have checked this this morning, and but no message until now.
And has Pete been in contact at all at the recently? Now, is there?
I seem to remember there was an email from Peter confirming that he was going to present, but that was a few days ago.
I got an email this morning from him, and sounds like he will join us.
Maybe he's got the times mixed up. Can I ask Greta a question then?
Sure, yes.
We're now getting lots of automatically generated data from other planets, mainly at the moment Earth and Mars, and some from the Moon. There's a massive amount of from the Mars orbital rover that is generating all sorts of interesting geoscience variables. I'm not sure. We've been working on landforms that you can infer from the data you get from the Mars orbiter, but it must be also be, at the very least, must be generating data that are proxies for minerals in the ground as well. Are you looking at extraterrestrial forms of data for this?
I looked a little bit at data from March, but not too much. But I talk a little bit about one of the papers we have. I talk a little bit about the different type of mineral species you have seen in March, and what type of minerals you see in Mars compared to what you're seeing on Earth. And for example, look like Mars, it's Earth-like when it comes to the mineral species, the type of mineral species you're seeing there. But I haven't really looked too much about. So far, I only kind of looked at mineral species on Earth. But I know that people in my research group will, in the future, look more about other mineral species from Mars. I know Shanna Morrison, she's a person I collaborate with a lot. She has been doing a lot more work with Mars, but I haven't been involved with that part. So, yeah.
Thank you, Greta. Thank you, Peter. So I think that we have Peter. Pete, you've joined us. Can you hear us, Pete? I definitely see your name up there. So possibly.
Yeah, I'm here.
Wonderful. If you want to share your screen, I'm just moderating the session this afternoon for me now. So if I can introduce just while he shares his screen. Professor Peter Atkinson is going to present the Distinguished Lecturer presentation for 2020. And obviously it's been an unusual year for both our distinguished lecturers for 2020 and 2021. And Jaime obviously presented the Crumbine Medal yesterday, but is also the Distinguished Lecturer for 2021. So the Distinguished Lecturer is a really important role for the IAMG in that it really is an awareness raising opportunity for mathematical geoscience. So Peter has been very active in person, but more lately, obviously, virtually sort of spreading the word from the IAMG, but also presenting a range of presentations. So Pete is a distinguished professor of spatial data science and also the executive dean of the Faculty of Science and Technology at Lancaster University. And has a number of visiting roles at professor at University of Southampton and also the Chinese Academy of Sciences at the moment in Beijing. His research interests are very varied, and I won't go through them. As I say, all of the bios for our speakers are on the IAMG website. But I'm going to hand over to you now, Pete, if you could present your distinguished lecture. Thank you. We can't hear you, Pete, just in case you're muted. Hi, Peter. We still can't hear you, but we can see your screen, your PDF.
Yeah. What can you see?
We can hear you now, and we can see your PDF, the screen, and it's a PDF on it.
I just can't hear you, Jenny. You're
Regina and Peter, can I just?
according to me.
Peter and Regina, could I check? Is it my internet or is it Peter's? I'm not sure.
It might be mine. It's most likely to be mine. I'm in a hotel.
Okay, we can hear you now, Peter, if you want to start.
Yeah, okay. I'll get started. Just shout if there's a problem and you can't hear me. Okay, so this is about representations, and it's a sort of call to step back a bit from the modeling and analysis that we all do. People like Isabel Clarke and Andre Janel have done a lot of work in relation to one element of this, and the point of this talk is to, what was done previously, in particularly in relation to the support. Let's see if I can, yeah, okay. So as Jenny said, this is one of the IAMG Distinguished Lecturer talks. In fact, I've done 6 already, and this is the 7th, so this will be the last one. And then Jaime Gomez Hernandez is the 2021 IAMG lecturer, so he's already started on that, I think. You all know about the IAMG, obviously, so I don't need to give this slide. Was promoting the IAMG as a fantastic organization that people can join, and explaining the benefits of it. Four journals now and the IAMG newsletter. The other bit of sort of selling that I wanted to do was in relation to Lancaster University, and say that I really like this photograph because it sort of explains the equivalent of 1,000 beautiful set location, then it's a great place for doing interdisciplinary. Get my brain into gear for this talk was a little bit.
Peter, we're sort of losing you sometimes.
To be honest, and I'm in the middle of decorating my,
Peter, if you can hear me, perhaps if you took off your switched off
a house that we rent out. So so apologies if this is a little bit scattered.